In this video, we present an overview of the Topology as a Service cloud or data center management system. Topology as a Service, or TaaS for short, provides a conceptional and technical framework to help enterprises or cloud providers design and build up a data center environment that supports portable, fully automated, and therefore speedy infrastructure and application delivery, fulfilling enterprise-level production quality. While you can find numerous products positioned as literally solving data center automation out of the box, larger companies struggle still with significant remaining problems. We will explore this gap first. Typically, even the pure technology setup, the automation of higher-level application services, integration into ecosystems, and not to forget lifecycle management or maintenance are conceptually challenging. But also the architecture standards and design guidelines for effective use and reuse across many applications are hard to get right, especially if these applications have to fulfill enterprise requirements like strong security, portability, auditability, high availability, or disaster recovery. A detailed discussion of some often cited business cases in data center automation should make the difficulties more clear. The Topology as a Service framework was explicitly designed to address the mentioned gaps. We discussed the framework's main features and how it fits into an existing environment through its modular design. In separate videos, we focus in even more detail on various important aspects of TaaS and include interactive demonstrations of the system. Finally, we explore how the main features of the TaaS framework benefit some important use cases. Overall, we discuss motivation, design, use cases, and benefits of Topology as a Service. We thereby strive for substance and comprehensibility and try to avoid unexplained and often ambiguous buzzwords. So let's now first look at the identified gap and some business cases exemplifying the problems in more detail. One of the most ill-founded beliefs often encountered in the IT department of a company, small or large, is that a new technology product will itself solve all problems. Despite glossy marketing brochures and shallow technology blogs, the reality is that just the purchase of a technology product is never enough. There is no magic, especially in the areas of data center automation or enterprise integration. Let us highlight some of the areas where we believe enterprises need to invest beyond pure technology. First, we denounce the myth that IT automation on a large scale can be achieved without appropriate architecture and strategy. Standards for a restricted set of supported technologies and for data center management processes are vital to avoid high variability that becomes unmanageable and expensive. Also, if you aspire to instantiate entire non-trivial applications rapidly and operate them effectively, you cannot rely on the typical fast provisioning of individual infrastructure parts and some software deployment toolchain. In addition, automated configurations across the entire dynamic environment are key to success. Portability of applications is often misunderstood. In the true sense, it means resilience against changes induced infrastructure products. That is not a trivial byproduct of a technology purchase. Careful abstraction design, along with its enforcement, help make the difference. If your applications need to fulfill enterprise requirements like strong security, auditability, and so on, it is not effective to let every application invent its own solutions. Instead, you need centrally managed, reusable designs and implementations with appropriate processes, support, and governance. Finally, application migration or regular lifecycle management can become prohibitively expensive if not taken into account early on. A company's long-term ID strategy can significantly reduce paralyzing vendor lock-in, long-lasting and expensive ripple effects by too early adoption of immature technologies, or cost-multiplying shadow IT bubbles. In summary, we see significant gaps between purchased products or technologies and the infrastructure service needs of enterprises and their applications. To expand on this point, let's now look at 3 examples of frequently cited but difficult to achieve business cases in the area of infrastructure service offerings. First, optimal capacity management is often seen as an important business case for a cloud, be it internal or external. If you do everything right, you can save a lot of hardware resources that you have to pre-purchase and to hold available for your applications. But that is a big if. The famous inequality that the sum of the peaks is greater or equal to the peak of the sums reflects the essence of this case. If you're not familiar with these terms, have a look at the footnote in the slide. In capacity management, you win if you can widen the difference between the two sides of the inequality. Important factors are increasing application elasticity and hardware utilization. The questions below might help you to shed some light on the situation in your company, but they should also point out where improvements can help achieve the overall goals. If it takes a long time to receive an application's infrastructure, and then still more time to bring the application to a fully functioning running state on that infrastructure, then nobody will give back temporarily unneeded infrastructure or work on effective elasticity. The other way around, however, the faster infrastructure orders are fulfilled, and the less work is needed afterwards to create a fully running application on top of it, the easier it will be for applications to realize elasticity and especially to give back unused hardware resources, be it in development, test, or in production. And if there are complex restrictions on how to place an ordered infrastructure element, for example, not with another application's elements on the same hardware, then it will be very difficult to optimize hardware utilization. The second business case we want to look at applies to technology lifecycle management. Introducing a new operating system patch, upgrading to a new minor or major release of a middleware product, or even replacing an infrastructure product by another with the same functionality should not cause a lot of undue costs. Especially if applications are not shielded from such changes, the costs can be multiplied. With high costs, the lifecycle decisions, for example for security fixes, cannot be taken independently just on their merit as they should be. The added questions highlight again the perceived pain points. You might be in a situation where your overall technology portfolio is very diverse and the reuse of engineered technology products is low. Or your applications might decide on their own which products and releases they want to use. In these cases, you may have a strong argument to centralize technology management, standardize on fewer but reusable technologies that are supported well and are enforced. Thereby, engineering efforts for product or release integration, as well as for application migrations, are significantly reduced, and strategies for avoiding vendor lock-in or enabling application portability become feasible. Operation management is the area of the third and last business case we want to discuss. Downtimes of applications can be very costly and should be either avoided or then fixed as quickly as possible. Automation plays a twofold role here. On the one hand, a common cause for downtimes and mistakes in manual steps for setting applications up correctly, either when they are first deployed or when runtime adaptations like regular scaling or occasional upgrading have to be applied. Such downtimes can be avoided by fully automated setup and runtime services. On the other hand, the still necessary handling of production incidents should be supported by automated repair services as well. This can help to reduce mistakes during incident resolution, to keep repair time as short as possible, and to prevent problems from spreading, for example via affected shared services. Automation for downtime avoidance or downtime repair requires that these services have access to and can interpret runtime environment data and metadata that is reliable and semantically rich enough to guide the services in their complex tasks. That information must reflect precisely which parts of an application are running where, in which state they are, how they relate to other parts, and which parts are shared across applications. If you have to guess about how to distinguish the origin of a problem from reported but secondary effects, or about possible ramifications of a runtime change, the operation risks are just too high. An IT security area of growing importance is microsegmentation, or application firewalls. Setting up a network firewall just around a part of an application is much less error-prone than maintaining a catch-all firewall around an entire production zone. Automation of such microsegmentation requires knowledge of the precise communication needs of application parts, not only on first deployment, but also repeatedly for every maintenance release. Detection or trial and error for such setups is not only costly, but also risks to either leave unnecessary holes in a firewall, or to be too restrictive, leading to later production incidents, for example for missed border cases. The new Technology as a Service framework is designed from the ground up to address the outlined gap between out-of-the-box technology products and comprehensive automated enterprise services in cloud or data center management. Accordingly, it encompasses not just a technical tool, but also architectural guidance on how to complement the pure tool to achieve the goals in an existing and evolving environment. Most importantly, it supports the creation of fully automated, comprehensive data center services for entire applications, as well as the implementation of the non-functional strategic goals pursued by an enterprise. At the basis of the TaaS framework lies the capability to create high-level, intuitive models of the entire infrastructure topology of applications. The supported automation services operate on these models and are customizable to be adapted to a given corporate environment, with its infrastructure topology products for application runtimes and ecosystems, as well as its architectural guidelines. The services encompass the lifecycle tasks of infrastructure topology management, as well as application software deployment with controllable sequencing of transport and installation steps across topologies. The services include the necessary configuration steps and ecosystem integrations and parallelize their tasks across topologies unless where dependencies necessitate serialization. The system facilitates a company's implementation of conceptual data center strategies like standardization of used technology products, application portability through abstraction, or process automation and enforcement. Topology as a service is composed as a modular system that cleanly separates concerns. The core is constructed as an object-oriented application framework in Java and implements generic orchestration algorithms on topologies that can be called from outside as services and generate or work on abstracted target resources. Callers of these services are development toolchains, automated workflows or processes, or even other infrastructure automation systems using domain-specific languages or scripting, and so on. There is also a graphical user interface included in the system that calls out to the core and allows users to specify and manipulate topologies interactively. Target resources created by the core are typically VMs, containers, or even meta-specifications that are then automatically fed to other resource creation systems. For individual narrow subtasks that require detailed knowledge of used technology products or imposed corporate standards beyond configurable properties, the framework calls generic default methods that can be overridden in environment-specific subclasses to implement the necessary customizations. Typical areas of such customizations are target realms and ecosystems. Let's look at target realms first. Subclasses there implement product-specific specializations and industry or corporate standardizations and guidelines for handling target resource layers or layouts. Typical examples of such realms are network, operating system, middleware, or database realms, representing either directly a particular product or just a general abstraction of the realm that needs to be further subclassed for specific products. Finally, ecosystem subclasses customize the system for specific products in the areas of CMDBs and inventories, software repositories, security management, monitoring, and so on. In order to facilitate a deeper understanding of the TaaS design and capabilities, some additional videos are provided that explain and demonstrate the most important features in more detail. The system with a full-fledged implementation of the core services and the interactive graphical user interface, together with sample implementations of some customizations of target realms, is running in a demo environment on a MacBook Pro. This environment uses, on the one hand, a desktop virtualization product running a virtual network and VMs containing components of a simple data center, a hypervisor, as well as DHCP and DNS servers. A second layer of virtualization is established on the hypervisor, where, for example, the customization VM templates reside and the dynamically created client VMs run. On the other hand, a native Java Enterprise server runs the TaaS framework that interoperates with the virtual data center, and native browsers are used for the GUIs of the TaaS portal and the generated client applications. Videos with further explanations and extensive interactive demonstrations exist for the topics of topology modeling, automated provisioning and software deployment services, as well as for the special TaaS feature of context configuration, which comes in two parts and with more complex examples. References on YouTube for these demo videos and also for this overview are added to the description section of each video. Searching YouTube for TaaSFW will also find them. The Topology as a Service framework design has been guided from the beginning to solve strategic enterprise use cases and business cases. Key features identified early on were high-level modeling, abstraction and customization, and comprehensive automation for entire applications. Application development profits from the ease of modeling and the high speed of the comprehensive automation in various scenarios. For one, individual code changes can now be tested very quickly in the context of the entire application in sort of a personal integration test. This is possible because the running application, including the new code, can be created very rapidly on fresh infrastructure. Then tests can be run and repeated after more individual changes and incremental redeployment, before the resources are released again. The feasibility of small individual changes that can be verified quickly within the entire application leads to better tested, more robust code. Similarly, continuous integration can be executed faster and more often, leading to accelerated quality-assured progress in team development projects. In addition, performance testing can be improved since it is easy and fast to try out and measure many variants of infrastructure setups. This can lead to more optimal infrastructure usage and/or better application performance than with conservative decisions that are based on assumptions rather than facts. Cloud business cases can now be realized because entire applications are targeted rather than just low-level infrastructure parts. The sweet spot of hardware free space minimization in a data center, for example, can be reached because returning capacity becomes a routine action in development, testing, and production. True on-demand usage of infrastructure becomes feasible if data center services for entire applications are fully automated. Also, applications can be more easily made portable and resilient against changes in infrastructure. Of course, enforced discipline and standardization are still needed in a company, but the support by the framework is crucial. High-level modeling, API and SPI abstraction, component reuse, and ease of customizations for differing environments help a lot. Finally, modeling and automation can simplify the operation of applications and make production environments more robust, whether they are managed by a separate operations department or often even more so by a DevOps organization. Typical examples are runtime services, like node replacement or scaling of an elastic tier. Since all necessary steps, including removal of creation side effects when deleting nodes, are fully automated, downtimes due to manual mistakes are much reduced. Production processes can be newly designed along the new capabilities. For example, application lifecycle management can profit from fast recreation of entire applications in an upgraded environment that can then take over from the previous setup. Even going back to a previous version that was deleted is possible. Error-prone updates or patches that are executed in place can be avoided. And because node connections are modeled in the topologies, precise auditable application firewalls can be automatically set up. If the model changes, adjusted firewalls are set up automatically on the next instantiation. In other words, the model is also the documentation. In summary, the TaaS framework implements a cloud orchestration system for entire applications and their infrastructure. The system is very rapid, comprehensive, and easily customizable for differing products and standards. It is itself portable, but also helps users create truly portable applications. As outlined in the use cases, the framework addresses mainly three target audiences. The first are application developers. They can model their overall infrastructure and software deployment needs intuitively and in abstracted terms. For that, they are reusing predefined parts from a catalog, which can be either ad hoc parts or corporate standard parts or even third-party products. Thereby, the application code can remain simple, portable, and free of unmanageable static context artifacts. Secondly, operators can profit because they gain insight beyond individual parts into overall structure and dependencies of running applications within an auditable CMDB and inventory. Routine operational tasks are supported by comprehensive automation services to dynamically create the structures, adjust them to changing conditions, and destroy them again. And finally, entire organizations can improve the implementation of their strategies. This can be large corporations, but also cloud providers that offer these services to their clients. They can obtain the means to customize the system to their preferred technology products and environment, and to enforce industry or corporate standards. Third-party adapters are supported as well. In short, the Topology as a Service framework enables fully automated, very rapid last-mile delivery and lifecycle management of entire applications and their infrastructure in enterprise production quality. The framework itself is portable and helps companies to make applications portable by supporting adaptability to varying infrastructure management products, as well as to differing target operating systems, middleware, and ecosystem products, and versions thereof. All this is achieved through the discussed features like high-level declarative modeling of entire application infrastructure and deployment topologies, rapid and comprehensive dynamic automation, and customizable data center integration and standardization.